Exercise 41.5. This exercise is to be solved manually. Consider the region enclosed by the graphs of y equals x cubed minus 4x squared minus 11x plus 30 and the x-axis. Part A. Sketch a quality graph of the described region. Provide a graphic approximation of the area of the region. Part B. Provide a calculus calculation that yields the exact area of the region. Part C. Assess the correctness of parts A and B by examining for consistency between the two results. Part A. Sketch a quality graph of the described region and provide a graphic approximation of the area of the region. Alright, well, being enclosed by these two graphs, the x-axis is pretty obvious, but what about the one on the left here? That's a cubic function, and when I see a cubic function with a positive ax cubed term, I'm expecting one of two basic shapes. One has only an inflection point, no relative extrema, and a second variety that has an inflection point and a pair of relative extrema. Since we, in this case, have some region that's enclosed by this graph in the x-axis, it's pretty much got to be this version with the two relative extrema. And it pretty much has to be intersecting the x-axis. So, that being noticed, it's time to search for X intercepts. For X intercepts, we would let y equal to 0, and the resulting equation is x cubed minus 4x squared minus 11x plus 30 equals 0. Okay, this is a polynomial equation, and for those, we have usually 4 lines of strategy we try to apply in order. First, extraction of roots. Second, obtain a factorization equal to 0. 3, a quadratic formula. And 4, seek rational solutions. So what about the present equation? Well, extraction of roots is nowhere in sight. How about obtaining a factorization equal to 0? That is a general cubic expression on the left there. It appears that factor by grouping might be a starting point here. Factor by grouping makes some people rather uneasy because it is a bit of an art and not everybody succeeds with it. However, when it works, it's fast. So let's try it here, and I will also provide a fallback strategy later on in this video using a seek rational roots method as well. But for now, let's try factor by grouping. For starters, let's take that minus 4x squared term and rewrite it as minus 2x squared minus 2x squared. Alright, this will leave us with 5 terms which we can group, 2 terms on the left and 3 terms on the right. The 2 terms on the left can be subfactored. We see a common factor of x squared, take that out, and on the right hand grouping, consider just taking the negative sign out as a factor at first. Now that right-hand trinomial further factors as the 2x plus 15 times x minus 2. This is very good news because look at the big picture. We see an x minus 2 as a common factor to everything. That can be pulled off to the side, leaving behind the other 2 quantities, which then become a trinomial, which then further factors, and we have then successfully completely factored the left-hand side, and now we have a chance to easily solve the equation of a factorization equal to 0. So, solving h factor equal to 0, I arrive at x equal to 2, 5, or negative 3. Then, to be courteous, I'll record the solutions in ascending order, so x equal to negative 3, 2, and 5. Okay, suppose factor by grouping was not a success for you. or perhaps you did not even care to try that to begin with. After all, it is a bit of an art. In this case, there is another method. You could go to what is sort of the final method in the manual solving of equations list, and that would be to seek a rational root. Taking a close look at the left-hand polynomial, some good news is that the coefficients happen to all be integers. This means this polynomial satisfies the hypothesis of the rational root theorem. What's that? You may recall that the rational root theorem says that if a polynomial has all integer coefficients and a rational number, p over q, is a root of the polynomial, then p is a factor of the constant term and q is a factor of the leading coefficient. What does that mean in more practical terms? The rational root theorem is telling us that the candidates for rational roots of a polynomial having all integer coefficients are those numbers which can be created by using a numerator which is a factor of the constant term and a denominator which is a factor of the leading coefficient. Why don't we try that here? We would have a list of possible roots whose numerator could be plus or minus 1, 2, 3, 5, 6, 10, 15, or 30. There's a lot of factors of 30, right? Now, those are numbers which could be divided by 1, plus or minus 1, because fortunately here the leading coefficient is simply 1. Okay, the next thing to be doing is to, by trial and error, substituting in these candidate rational roots to see if any of them actually work. So it's time for a pre-calculus review, and that is that, did you know there is a choice of methods when you're computing the value of a polynomial? You can either use direct substitution, which is what you usually use for everything else, but there's also this synthetic substitution method available, and it works by actually dividing the polynomial by x minus c and grabbing the remainder as being equal to the p of c. How can that be? Well, there is this remainder theorem that says if a polynomial p of x is divided by x minus c, the remainder will equal p of c. Also, there's another item, and that is that for performing the division, instead of using the usual long division process, there is a special type of fast, efficient division process called synthetic division. It's especially suited for when you're divided by x minus c, and that's the one everybody uses when performing a synthetic substitution. Okay, time to return to our question at hand. So now, using synthetic division, I'll find the value of this polynomial at x equal to 1. Now, you might think x equal to 1 is so trivial, I could just use direct substitution and obtain the result in just seconds, which is true. However, the synthetic division gives me additional information, namely, if in the event that x equal to 1 causes the value to equal 0, and then it's a solution, I would like to divide the polynomial by x minus 1, and if I've done my synthetic division, I already have the quotient if I proceed this way. So here we go. We want to find the value at 1, so 1 goes off in a box here on the side. Now the coefficients of the polynomial, they are 1x cubed minus 4x squared minus 11x and 30. Leave a space and a bar. Drop down the 1, multiply 1 by 1, get 1, add the column, negative 3. Multiply 1 by negative 3, negative 3, add the column, negative 14. Multiply 1 by negative 14, negative 14, add the column. It's positive 16. This is the value of the polynomial at x equal to 1. It's not 0, so we have not got a success here for finding a root. However, we have a little more information in our hands now. We did find that y of 0 was 30. Moving to x equal to 1, the value drops to 16. This graph seems to be decreasing, perhaps, and so perhaps x equal to 2 will give us some success. Well, let's try it. Same procedure, synthetic division. 2 in the box. The coefficients, 1, minus 4, minus 11, and 30. The space, and drop the 1 down to begin. 2 times 1 is 2. Add the column, negative 2. 2 by negative 2, negative 4. Add the column, negative 15. 2 by negative 15, negative 30. Add the column, 0. There we go. So, we have found that x equals 2 is a solution to our polynomial equation, and we've already got the division completed, dividing the polynomial by x minus 2. Here is the quotient with its coefficients. In other words, we now have the reduced equation. We have the x minus 2 from before, and now we have 1x squared minus 2x minus 15. That now equals 0. Alright, our attention goes here. Can we factor this further? This is just traditional factoring methods. Two numbers whose product is negative 15 and sum to negative 2. Negative 5 and positive 3 come to mind. Check that. Product, negative 15, and sum is negative 2. Okay, there we go. And now we can solve each factor equal to 0 and have x equal to, alright, it would be 2, 5, and negative 3. I'll put them in ascending order. Negative 3, 2, 5. Okay, and now I am at the same point as I was doing our other solution. So the first thing I do with these x intercepts is I graph them on a real number line to help me think what I need to do next. Because I know that we have a cubic function with a positive ax cubed term, I mentally form this image of the basic graph shape as being about like this. And this tells me what I need to do now, because we're looking for the region bounded. I need to get points on the graph that lie between x being negative 3 and 2, and some more points lying between x equal 2 and 5. Luckily, it looks like just by choosing integer x's, I can get enough points to get a pretty good quality graph. So, that's the next plan. So for computing the corresponding y-coordinates, I've actually got a choice. This is a cubic function. So, that means as it's a polynomial function, its values can be computed one of two ways. Direct substitution, which is what everybody is completely used to, or synthetic substitution, which can save virtually 50% of the arithmetic. Okay, in this case, the polynomial function has pretty simple integer coefficients. The x's I plan to compute with are very small integers. Okay, that being the case, I'll choose direct substitution this time, but that's not always the best choice in the realm of manual computing. So here's the results of those direct substitution computations of y at the various x's, those integers that we pointed out previously. And now looking at the y values, the least appears to be a negative 14. The greatest looks to be 36, so that's a span of 50 units. Let's say we'd like at least a 12 centimeter y-axis, so this will mean about 4 units per centimeter. Okay, so we'll choose a y-axis to go from, say, negative 16 to 40 at 4 units per centimeter, and we'll have the x-axis go from negative 3 to 5, and we're ready to start graphing. There's our planned coordinate system. First graph those x-intercepts, then graph all those intermediate points we calculated with direct substitution, then connect the points with a smooth curve, then shade the enclosed region, then label the important graph, and finally label the enclosed region. Done. It's time to approximate the area of this region. Looks like it's going to require two geometric shapes to accomplish this. And I also need to be a little careful here because the axes are scaled differently. The x-axis is scaled at 1 centimeter equals 1 unit, while the y-axis is scaled at 1 centimeter equals 4 units. Thus, the geometric shapes I select need to have their key measuring dimensions parallel to an x or y axis. So looking at the situation here, maybe rectangles could be okay, or triangles, pretty good, but I find the more tightly I approximate, the better the approximation. So I am going to go with a pair of trapezoids here as the approximating geometric shapes. When sketching this final base, I look to see that the area that's being excluded would just equally fill the voids that I have in the shape. Here I want to write down that the approximate area of the enclosed region is the sum of the areas of the two dashed line trapezoids. Now, to get that area, I have to remember the area of a trapezoid. For me, my mnemonic device is to just say its average base times height, which translates into a 1/2 of B1 plus B2 times h. Here I measure the height with the ruler in centimeters, but I momentarily forget to realize that the y-axis is not scaled 1 unit per centimeter, it's 4 units per centimeter. So momentarily I have an error here. However, when I come to measure the height for the other trapezoid, it occurs to me that I have made a mistake there, and I am able to compensate, or fix it rather, by multiplying by 4, which converts the 8.3 centimeters into units in the y direction. Now it's just arithmetic to finish it out. There we are. Got 144 square units for the graphic approximation. Part B. Provide a calculus calculation that yields the exact area of the region. To use calculus to find an area, you slice up the region and sum up the areas of the slices. Let's try slicing up this region with the most popular thin vertical rectangles and see what we think. Not bad, but there is a bit of a problem. Watch the tops of the rectangles as we proceed across. They start off with their tops being determined by the cubic function graph, but then there's a change. The tops of the rectangles become determined by the x-axis. The bottoms of the rectangles undergo a similar situation. They start off being determined by the x-axis, then there's a change. They become determined by the cubic function graph. Okay, as far as getting the dimensions of a thin vertical rectangle goes, this actually would lead to two different formulations, which we can't have. We'd have to use two different integrals. One way out of this might be to say that the length of each rectangle is the absolute value of the quantity y minus 0. But remember, we're solving manually. Do we know of any antiderivatives of absolute value of f of x? No. All our antiderivative formulations rely on us just simply having f of x type functions. Okay, so looks like we're going to need to go to two different integrals and sum them to get the overall area of this region. The first one, which will sum the thin vertical rectangles on the left, we'll have thin vertical rectangles whose height is y minus 0, and the thin vertical rectangles on the right will have a height of 0 minus y. In both cases, their width will be a little piece of x-axis, dx. Notice the previously calculated x-intercepts are indeed the limits of integration. So the left-hand integral is going to sum with dx going from -3 to 2. The right side integral will sum with dx going from 2 to 5. Okay, we are ready to formulate. What we have for our two integrals are the following. And then we can rewrite this a little bit more simply. Okay, and perhaps now our first sort of sub-calculation. I'll put an asterisk and refer the reader down to here. And we will now consider the indefinite integral of y dx, which is... And for this, we need only use power rule successively. So this would be, let's see, x to the 4 over 4 minus 4x to the 3 over 3 minus 11x squared over 2 plus 30x. It's an indefinite integral. It's supposed to be recording all the antiderivatives, so a plus c to accomplish that. We would like to use the one simplest antiderivative here. Here's us. Let's call this cap f of x. And proceed back to our main equation. Looks like then we're going to have this being cap f evaluated at 2 minus cap f evaluated at -3, subtracting cap f of 5 minusing cap f of 2. And that actually simplifies a bit. That could be, this is a minus a negative that's adding an f of 2. That gives us 2 f of 2's. And then minus an f of -3. And then minus an f of 5. So now we have a sort of a second phase of subcalculation. And that is to get the value of f. These, well, we have 3 evaluations to perform here. I suppose, since f is a polynomial with fractional coefficients, synthetic division could be quite helpful in reducing our error chance considerably. So let's go ahead and go here to start computing the various values here. For instance, f of 2, using a synthetic division process, we get the coefficients of our f here as being 1/4 minus 4/3 minus 11/2, 30, and notice there's a missing constant term in f, so we need to make sure to put a 0 to complete that there. And here we go. Multiply, add, need to go to 6th here, 2 over 2, 3 over 3 build up there, minus 8 of them, plus 3 of them, minus 5/6, times 2 here, means minus 5/3, need to go to 6th for these guys. So this gives a 3 over 3 buildup, a 2 over 2 buildup here, minus 33, minus 10, minus 43, times 2, minus 43/3. This would be 90/3 minus 43, brings us down to, let's see, 47/3. Check that again. 90 minus 43. Yeah, okay, 47/3. Okay, times 2. This puts us at 94 thirds. Sum 94 thirds. Okay, there's our f of 2. That's in order. Let's get a similar synthetic division to get f of negative 3. Main equation, okay, 2f of 2's. 2 of these, okay, 188 over 3 minus the f of negative 3. That'll be then plus 333 over 4, minusing the f of 5, minusing 25 twelfths. Square units. Okay, so there's our calculus area. Part C. Assess the correctness of parts A and B by examining for consistency between the two results. To assess correctness, we should review the results of parts A and B side by side. First of all, let's go back to that graphic approximation and see what we had for that. Looks like we had 144 square units. Make a note of that. Now, let's again take a look at our calculation. What do we have for that? That was 863 over 6 square units. Let's make a note of that. Now, for comparisons, we're going to need to do a bit of long division here to see what 863 over 6 actually is. Okay, 143 and 5/6. Wow, compared to 144, those two results are within 1% and certainly consistent. With such consistency, we're pretty confident in saying that the solutions to part A and B are very likely correct. Alright, that completes exercise 41.5. Congratulations.